Bharati, good evening. Konal, Krishna Reddy, everyone. Not listening to what I said. So let me upload the slides. I think you are asking the question but not listening, Yadav. I have answered your question just now. Right? Remaining people, please tell what I said. Yes. Okay, Yadav. We'll discuss that at the end of the class. Any general queries at the end of the class. Yeah, first we are doing yesterday's homework only. No problem, I am there. I will solve it. I didn't ask the answers. Please don't comment. I will turn on so that you can ask the doubts and so that the class will be interactive. But if you comment without asking the question, okay, don't comment the answers. It is not the right habit. Everybody in the class should enjoy the class. Okay. So let's start with this question. A binary, okay, coded pentry number system is proposed in which every base 5 number is represented by its 3-bit corresponding binary code. For example, 24 is represented as 010 100. Now, examiner question is, in this number 5 system, what is this number? It is a very simple question. I hope most of you done. Now comment, please. Now comment. Everybody done the question? Very good, very good. So what is the answer? 100 010 011 001 is the input given by examiner. Okay. I'll conduct the poll also, don't worry, depending on the question. So what is the statement of the question? Base 5 system, every 3-bit is replaced by its corresponding code, 3-bit binary code. So here 24, 3 bits is 2, 3 bits is 4. Similarly, replace every 3 bits with one number. Pentry means nothing but base 5. And that doesn't matter for us. So every 3 bits replaced with its equivalent. 011 means what? 3. 010 is 2. 100 is 4. That's all. Is it clear to everyone? Yes, base 5 only. Okay. So let's move to the next question. Yeah, you can ask deep. Please ask. Please ask. This question I'll conduct the poll. Be ready. Yes, Akash. In base 5 or base 4, whatever may be, 011 is 3 only, na? Base 5, okay. It is nothing but in the base 5, you will be having the numbers 0, 1, 2, 3, 4. 5 will be represented as 10. If you have 5, you will see the difference. 1 to 4 will be same only in the base 5. In the base 5 up to 4 same. From 5 you can see the difference. I hope you understand this. Base 5. Okay, base is nothing but radix. Yesterday we have discussed, right? Is it clear, Deep? Okay, fine. So please tell me, I mean, you can start, I will start the poll. Is it okay? Can you start the poll for this? Okay. Okay. So let me start the poll. Answer. Very good. Okay. The poll time is getting fine. See here your results. Sagar, you are the first one. Rishikesh, Abhinay, Kuldeep, Mohan, Deep, Suraj, Abhineet, Konal, Khan. Okay. So how to do this question? I never suggest here, no one will suggest you to calculate this total value and convert by dividing with 2. That will end your exam time totally. So how to do this question? I will show you two different ways to solve the question. First one is, you can write this number as 4 into 16 power 3, 9 into 16 square, 7 into 16 power 1, and 5 into 16 power 0. Is it okay for everyone? So this is nothing but 4975 in the hexadecimal. It is nothing but 4975 in hexadecimal. I hope you remember yesterday's class. Positional value r power 0, r power 1, r power 2, r power 3. R is 16 here. You are replacing. Okay. Then you convert this into binary number. How to convert hexa into binary? Replace every digit with 4-bit equivalent. 4 means 9 is 1001. 7 is, and your 5. That's all. So how many ones are there? 1, 2, 3, 4, 5, 6, 7, 8. This is one method to do this question. Okay. I will give you another method also. Before that, see this question. Firstly, tell me, is it clear for everyone, this question? I'm again repeating, even every single person in the class said yes. Still you have doubt, ask. Okay. Don't hesitate. My class, you should not hesitate to ask the doubts. Okay, fine. Come here. How to do this question? How to do this question? 3 into 8 cube, 7 into 8 square, 5 into 8 power 1, 3 into 8 power 0. That is nothing but 3758 in the octal. How to convert this into 58? I'm sorry, 3753 in the octal. What is the binary conversion? 3 should be written as 3-bit equivalent here. 3-bit equivalent is 011, 111, 501. So 369. Okay. Is it okay? Fine. Now let me give you another way to solve this question. We may not give you every time by octal and this thing. We may give you a different way. You should be able to answer it. Say for example, if you have in any number system with base r, okay, r power n is nothing but 1 followed by n number of zeros. 1 followed by How many zeros you will be having? N number of zeros. How, sir? Simple example. Just come to your basic number systems of what is 10 power 3, my dear friends? What is 10 power 3? 1 followed by 3 zeros. What is 10 power 5? 1 followed by 5 zeros. I want to give small shortcut also here. Okay. Now, 1 second. What is 2 power 4? 2 power 4 is 16 na? 16 is equal to 1 followed by 4 zeros in binary. Similarly, what is 2 power 3? It is 8. What is 8? 1 followed by 3 zeros. That you can understand in any number system with base r power n is nothing but 1 followed by n number of zeros. Is this point or concept clear for you? Very good, Asif. So thank you, Asif. Yesterday you have dedicated one hat for me. Thank you very much. Just to see the your screen, please see the screen. If you have any number system, r power n is nothing but number followed by n zeros. In binary, 16 is written as 1 followed by 4 zeros. In binary, 8 is represented as 1 followed by 3 zeros. Please understand here, in any number system with base r is the base of the number system. If you take decimal, I am saying this is decimal. In the decimal, 10 power 3 is 1000, na? 10 power 5 is 1 lakh. Similarly, in the binary, 2 power 4 is 16, 1 followed by 4 zeros. 2 power 3 is 8, 1 followed by 3 zeros. Now clear? Here r is nothing but your base. Any number system, same rule. Okay, you take octal also. 8 power 3 is nothing but whatever you calculate this 8 power 3, 1 followed by 3 zeros in base 8. Because it is r power 0, r power 1, r power 2, r power 3. Same rule. 512. You can check it if you want. No doubt in it. Now, one more thing. What is 25 into, that I am speaking decimal only, 25 into 10 power 3. What is the answer? I will apply in this question now. 25,000. 55 into 10 power 5. What is the answer? 55 followed by 5 zeros. So from this also you can derive one relation like this. If you have one number, multiply that number with 10 power n. Then what is the answer? 1 minute please. Here 10 is a decimal. If you have a number, multiply that number with r power n. What is the answer you will be getting? Number followed by n number of zeros. Is this relation correct or not? Tell me. I will prove in binary also if required. Firstly, tell me. Number multiplied by 10 power 3 is number followed by 3 zeros. So number multiplied by r power n is number followed by n number of zeros. Very good, Kunal. So, for example, you have 5 into 8. Can I write 5 as 2 power 3? Yes or no? 5 into 2 power 3. You try to convert into binary and check it. 40 is equal to this much. Okay. 5 into 2 power 3. It is 2 is the binary. Okay. R power n. So 5 is 101. 3 zeros will come. This is the shortcut. In any base, number followed by number multiplied by r power n is number followed by n number of zeros. As if it should be 5 into 8 power 3 in that case. If you have in octal, if you want, I will give the example. Suppose if you multiply with 5 into 8 power 3, it will be 5 followed by 3 zeros in octal. Okay, if it is 5 into 8, 50, correct, Asif? Right. So let me use this. This is Kumari, this is the same point. If you have a number multiplied with base power n, then number followed by n number of zeros. See here, 25 into 10 power 3 is 25 followed by 3 zeros. Similarly, 5 into 2 power 3 is in the binary 5 is 101 followed by 3 zeros. Is it okay? Thank you, Deep. Kumari? Okay, right. So now come to that question. Whether it is hexa, octal, now you need not worry about it. Simply, what is the question? 4 into 4096 plus, okay, they can give now combination also, you will be able to do. This and this together they give, you will be able to do now. So 9 into 256 plus 7 into 16 plus 5. Okay. So can I write this number as 4 into, you should remember some at least 2 power n's. Okay. It is 2 power 12. 2 power 2 is 4. 2 power 10 is 1024. So you can say it is. So 9 into 2 power 8. 7 into 2 power 4. 5 into 2 power 0. So in the binary, I am taking 2. Okay, I want to convert into binary. What is the simple answer? 4 followed by 12 zeros. 9 followed by 8 zeros. 7 followed by 4 zeros. And 5 followed by no zeros. Your job is done simply here. 1 0 1 0 triple 1 0 1 0 0 1 1 double 0. So how many you got? Number of ones 5 plus 3 8 is the answer. In this case, whether it is hexa, octal or mixture also you will be able to do now. Previous method is not applicable if the question is a mixture of octal and hexa. Now whatever may be the condition, don't worry about it. Write it in the form of 2 power n, your job is done. When you are converting into binary. Thank you, Aditya. So if you have doubt, please ask me again. I can explain. I can help you again. No problem for me. So let me just a few seconds. Let me revise it. If you have, okay, r power n into number, our method is a number followed by n number of zeros. Thank you very much. So number followed by n number of zeros. So using that concept, I replace 4 into 2 power 12, 9 into 2 power 8, 7 into 2 power 4, 5 into 2 power 0. Okay. So number followed by n zeros, number followed by n zeros, number followed by n zeros, and add it. Simple way to convert it. Thank you, Aditya. Thank you very much. So let's move further. Okay. Thank you, Khan. Okay. So shall I start the poll for this question? I have given it as homework yesterday. If you are ready, I can start the poll. Ready? 2 power 10 is enough. 2 power 10 is 1024 is just 1 kb. You should remember up to this. If you remember, able to remember, 2 power 12 is can be remembered as 2 power 2 into 2 power 10. 2 power 2 is 4 now. 4 into 1024. That should happen in your mind. Definitely, Sai. So here radix doesn't matter. Okay, here radix is decimal only. In all these cases, radix is decimal. Please understand. I am saying in this question, if both are given also, this is given, this is added, both are added, for example. Okay. For this, for example, 3 into 512 is also given. This also you can write 3 into 2 power 9, 4 into 2 power 12, and so on. So the process will be same. Akash, is it clear? I will give, don't worry. In the DPP, I will provide you. Tomorrow onwards, every day I will provide the DPP. Don't worry about it. Okay. So let's start the poll here. I hope you have done, because the examiner question is in binary. Just wait, keep it with you. In the last, I will share. I will discuss. Deep con. 1 minute. Let me go through the previous one. Just add all this. That's all. To get the original number, what to do? Just add all this. 5. This one. Add all this. You will get the final number. Now come here. Let me go a little slow for the second year students. Okay. So question is, well, I didn't understand what you are asking. Sir, previous question with breaking each number of terms of 2 written only in powers of 2 and add and counted them. Please understand, that's what I am saying. This is given by examiner. Okay. He has converted every number into multiplication of 2 power n. He don't expect you some other number to go solve it. Okay. So he made this part. We should answer from that. Just take this as a break it into 2 power n's and add it. That's all. So here, please see, the question is root 121 is equal to 11. Then what is the base? Root 121 is equal to 11 in which base? So you know, square both sides. 121 will be equal to 11 square. This is your base. Okay. Now, how to write the equation for this? Yesterday we have discussed r square plus 2r plus 1. Here, r power 0, r power 1. R plus 1 whole square. Is it okay? Is this point up to this okay or not? Right. Now, you see, expand this right side equation. R plus 1 whole square is r square plus 1 plus 2r. A square plus b square plus 2ab. Is this relation valid for any r or not? True for any r. So it need not be 10. 10 can be one answer. It is true for any base. Any base. But you have already used 2 here. If you have 2 in a digit, your base must be greater than 2. Because in any number system, yesterday class, we discussed we can have the numbers from 0 to r minus 1 in each digit. So what is the answer? It can be any base greater than 2. There is r plus 1. Yeah, that is what we are discussing, Rishi. Vishwa is not there. I think he is attending Hindi lectures. Okay. Because now Hindi batch also same timing. So now the next question is similar model. Root 311 is I'm sorry. Root 311 is equal to 14. Then what is the base? Will you answer? Shall I start the poll? Okay. Shall I start the poll? Okay, I'll wait. I will wait. Don't worry. So meanwhile, let me upload the few slides of Nidhi. My Hindi batch networks is already done. In my profile, it is there in the recorded version. You can go through it. Just follow my profile. It is under with the name of Mission Gate 2021. So let me start the poll. Answer. Okay. So yeah, most of you 29% has given right answer. Okay, so it's gone. I'm sorry. So let's see. Let's see how to do. I don't know R. So same rule. 311 is equal to 14 square. Square both sides. Now 3 into R square. R plus 1 equal to R plus 4 whole square. So it is A square plus B square plus 2AB equal to 3R square plus R plus 1. Take this other side. 2R square minus 7R minus 15 is equal to 0. Calculate R, you get 5. This is true for 5 only, not for any value. Is it clear? This is not true for all the bases. You will be getting this true for only base 5. You understand the difference between previous question and this question. Here it is true for any value of R, LHS equal to RSH. Here this is true only for R equal to 5. So these are the two different ways he can ask you the question. Okay. Yeah, here only 5. So let me upload the next part of your, just give me 1 minute. Just 1 minute, let me upload it. What happened? Okay. Nothing, just I need to upload some slides for your next topic. That is in another laptop. Some copies to came. That's why I'm waiting. It's going to be done in a minute. Don't worry. So let's start. Let's continue meanwhile. Yeah. So the next topic we are going to discuss in this number systems part is R's complement and R minus 1's complement. Here, what is R? What is R? Yeah, radix are base of the number system. Why do we need this radix or base of the number system? I mean, why do we need this R's complement? Okay, so what is the requirement for applying this 1's complement, sorry, R's complement or R minus 1's complement? You might be listening about already, you might be hearing about 1's complement, 2's complement, okay, right? Similarly here, R's complement and R minus 1's complement. Original reason for doing this is, yes, subtraction to represent negative number. But can you, why can't you do subtraction directly? Why this complements? I am asking, why can't you do direct subtraction? Is there any advantage if you use this complement and do the subtraction? Sign representation, calculation easy. Computer can't understand. Why addition is easy, Simran? Somehow you are right, but yeah, not addition is easy. We can do both the operations using addition. Suppose you have a machine which can do addition and subtraction. I don't need two separate hardware. Please listen. I need hardware for adder and separate hardware for subtractor. One method. Everybody listen, please. I want to do addition. I need one separate hardware. For subtraction, I need separate hardware. Is it suggestible, or for both the cases, only one hardware circuit? Which one is suggestible? Definitely, if you have only one circuit which can perform both addition and subtraction, which is advantageous for us. So we'll go for that particular case. That is possible with the help of this. How it is possible, everything we'll be discussing next. Now, yes, your slides uploaded. So let's start the topic. Just wait, Asif. Don't need. I will explain. Okay, compared to that, this hardware is less. So first we should start with, yeah. You maybe hardly require one inverter. Compared to a big circuit, inverter is efficient, easy for us, cost effective. So now see here. This is a fundamental definition of your R's complement and R minus 1's complement. Please go through this. I will explain. First, R's complement, what is another name? Radix complement. What is R minus 1's complement? What is R minus 1's complement? It is a diminished radix complement. And another name only, because if examiner give you diminished radix complement of this particular number, you should not confuse. Okay, it is nothing but R minus 1's complement only. Okay, I'll give a easiest shortcut for this. Don't worry about it. First, any number system with base R contains two complementary representations, that is R's complement and R minus 1's complement. R's complement of the number is nothing but R power n minus number. Wait. What is R power n? I told just now. Just now I told previously. What is R power n? What happened here? No comments. Right, deep. 1 followed by n number of zeros minus number is the way to write R's complement. Its advantage we'll see. Don't worry about it. Okay, next. R minus 1's complement. R minus 1's complement is R power n minus 1 minus number. That is just subtract one number from this. That is, please listen. Now, if you have 10 power 3, it is 1 followed by 3 zeros. What is 10 power 3 minus 1? My dear friend, tell me. What is 10 power 3 minus 1? Right, 999. Similarly, what is 10 power 5 minus 1? 10 power 5 minus 1? 9999. Okay. So 2 power 4 minus 1. Can you tell me what is 2 power 4 minus 1? 15. So in the binary, what is 15? In the binary, what is 15? 1 1 1 1. Okay, let me stop. Or you want, I can give one more example. 2 power 3 minus 1 is 7, which is 111. So what is the information you are getting from this pattern? If you observe this pattern, I am getting one idea. R power n minus 1 minus number is R power n minus 1 is nothing but Here it is 999. Here it is 111. You can say simply it is r minus 1, r minus 1, r minus 1. How many times? N number of times minus number. It looks complex, don't worry. Very easy to calculate. Just okay, formula looks complex, don't worry about it. What does it mean? Suppose your base is r is the base. If base is 10, 9999 minus number. If base is 2, if base is 2, 2 minus 1 is how much? 1111 minus number. Okay. So how many times you will be getting this? N times. Where n is, what is n? Number of digits. 5-digit number, n is 5. 6-digit number, n is 6. Okay. You can also say one more thing. What is the difference? What is the relation between these two? What is the relation between these two? R's complement is equal to r minus 1's complement plus 1. Accepted or not? Yes. There is no, just only one bit difference, one number difference. So if you are okay, I will move further. In this slide, no doubt na, for everybody. Nanda, you are there? So it's clear? So, okay, we'll move further. We'll move further. Okay. Now see here. How simple it is. Suppose, for example, you take decimal number system. In the decimal number system, what is your R? 10. For example, let me take a number 1, 2, 3, 4. In which number, which base? Decimal number system. Suffix is giving you base. Okay. In the decimal number system, this is your number. What is the number of digits? Number of digits, how many digits are there? My dear friends, tell me. 1, 2, 3, 4 digits are there. So now, what is our 10? Na? So 9's complement. How to find 9's complement? Simple rule. 9's complement is subtract the number from all 9's. That is 10 power 4 minus 1. Simplest format. Subtract the number from all 9's. 5, 6, 7, 8. Okay. Is it clear now? Then what is 10's complement? 10's complement is, here you should specify the base. Okay. Your 10's complement is, yes, 9's complement plus 1, that is 8766, or 10 power 4. 10 power 4 is how much? 1 followed by 4 zeros minus number. It will give you the same answer. Its utility we will see just next when we do the arithmetic operation. Yeah, n is the number of digits, Samira. N is number of digits. Is it okay now? 9's complement is very simple. Now, if you have octal, that is r equal to 8. Suppose you take the similar number, any number you take, 1, 2, 3, 4 in the octal. What is the 7's complement? 7777 minus 1, 2, 3, 4. Finish your job. Right. Similarly, what is 8's complement? Add 6543 and 1. 6544 with base 8. Okay, this is in base 8. That much simple. So now let's come to your Binary. 8's complement is 7's complement plus 1, Krishna. Anytime R's complement is R minus 1 plus 1. Krishna, you see here, what is 10's complement? 9's complement plus 1. Similarly, here, what is 8's complement? 7's complement plus 1. There is 7's complement number is there, add 1. Is it clear, Krishna? Similarly, you can do binary also. That is base equal to 2. Okay. Base equal to 2. Now see, again I am repeating the same process. For example, you have a number 1 0 1 0. Your base is 2 now. What is R minus 1? 1's complement. 1's complement is subtract the number from all ones. So 1 minus 0 1, 1 minus 1 0, 1 minus 0 1, 1 minus 1 0. That is here simple shortcut, 0 becomes 1, 1 becomes 0. Okay, next. What is 2's complement? 2's complement is 0 1 0 1 plus 1. That is 0 1 1 0. Is it okay for everybody up to this? As someone asked me to repeat, it's the same process. I hope from this example you might have understand. If you have doubts still, you can ask. Okay, clear. So let's move. Octal case, base is 8. In the binary case, base is 2. By method 2, you want, see here. Method 2, if you want, I can do. 8's complement is nothing but 1 followed by 4 zeros minus 1, 2, 3, 4. Here, please see. From 4, you cannot subtract 0. Okay, that is from 0, you cannot subtract 4. Take 1 borrow here. If you take a borrow, it will become binary. You have studied decimal number system. You have studied now. It will become 10. Okay. So, but 10 is nothing but 8 here. Okay, I will repeat this part. Don't worry. If you have 13 minus 5, you cannot remove 5 from 3. So, what you take from the elementary maths, you should take 1 borrow. That borrow will become how much here? 1 0. 10, 13 minus 5 is 8. 1 is given here 0, 0 minus 0, 0, 1 minus 1, 0. This is how you do it. I hope you know it, right? Similarly, in the octal, when you move the position, earlier you got 10 here, now similarly you get 1, 0, but this is equal to 8 in the octal. So 8 minus 4, 4. You cannot give 1. So here you should bring from higher order like this. So you should bring here 8 will come. 8 say 1, you remove it. 1 is given. What do you have? 7. 7 minus 3. Okay, 6 like this. Now they will provide the base as if nothing is provided, assume it as an octal. Definitely they will provide. Asif, okay, you will be definitely, that is a good question. There is a possibility in the base 9 of 8's complement is different, in the base 8, 8's complement is different, right? Definitely they will provide it, don't worry. Nothing is specified, you assume it as a standard of octal. Okay, 8's complement means octal. 9's complement is decimal. Okay, but they should provide in general. Okay, now come here. Up to this part clear? For example, I want to 2's complement of okay, 1 minute. How to find 2's complement of this number, my dear friends? Tell me. Take 1's complement plus 1. Now 1 plus 1 is sum 0, carry 1. 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 And 1, 1, 1, 0. This much job is to be done. I'll give you an easy method for this. Okay. Similarly, if you have 1, 0, 1, 0, 0, 0, 1. Okay. Now, how to find 2's complement? 1's complement is 0, 1, 1, 0, 1, 1, 1, 0 plus 1. What is the answer? 1, 1, 1, 1, 0, 0, 1. Okay. So now what is the shortcut? I want to provide you easy calculation is simply see here. 1, 0, 0, 1. All zeros are there. Na? To find 2's complement, simple method is see here. From this side, you go like this until you touch 1. Until you touch 1, you go like this. When you touch 1, write the number as it is. Remaining part is complement. Remaining part is complement. This method also will give you same answer. You see? Same answer or not? What is this method, sir? I will repeat with the another example. Please see. 1 0 0 1 0 0 1. 1 0 0 1 0 0 1. Okay. So what to do is start from the LSB, lowest least significant bit. Touch the first one. Touch the first one. Write it as it is. Remaining numbers, remaining bits, take complement. Complement means 1 will become 0. This is easiest way without any calculations. Without any calculations, easily you can do it. Okay. Similarly, if you have a number, okay, whatever may be the first digit, I have already cleared your Jahra. Okay, same, your doubt is cleared now. From here, you see up to first one as it is. Remaining, you take complement 0, 1, 1, 0, 1. Your job is done. This is the easiest way to find the 2's complement. Yes. Because 1 will become 0 will become 1 only for 1's complement. From that, we can do this for 2's complement. Okay. Simple rule. From the rightmost LSB, see wherever you get first one, up to that copy as it is. Nidhi. Remaining numbers, remaining bits, complement it. From here, you see the first one, up to that you copy as it is, remaining complement. See, wherever it may be in the starting, it may be in the second, it may be in the middle. Up to that, copy as it is, remaining, you take the complement. Okay. Same rule here also, it will be same because once it adds 2 ones, it will give you 0 and complement. This process can be simply written like this. Hi Raj, Hare Krishna. You came late or what? Which one? Priti, please see. This is binary only. Thank you, Bhargavi. This is binary only. Before this, we are speaking about octal. Okay, here your base is octal. If I write here 100, I should write the base. Definitely, examiner will give you the base. Okay, so that's all. So let's move further. Listen here. In decimal, we'll add 1 after decimal in LSB. I didn't get you what you are saying, Avneet. Okay, so I don't want to, please listen. I don't want to prove that R's complement will do subtraction with the help of addition. Now, just wait for some time. I will prove that. Just wait for some time. I will be proving those conditions. Okay. Is it okay what I'm saying? When I'm discussing about the arithmetic operations, there I will clear your doubts. That is how this will be helpful for subtraction. We'll discuss that. Okay. How this process can be helpful for subtraction, I will be coming to that part just after some time. Okay. Right. I will develop Saurabh. Okay. You also try to develop some trick. Okay. I don't have a ready-made for the fractional part. Now listen here. So the next part, BCD codes. Binary coded decimal. You want that also, Krishna? No problem. All complements are available. Just give me, let me give you one thing. Let me clear his doubt. Saurav, directly convert it. Okay. From the conversion, if you find some trick, we can find it. We'll see in the doubt session if required. Okay. Now listen here. If you want hexadecimal also, R equal to 16. A hexadecimal contains, okay, you have a number 1A, 2F. What is the number of digits here? 4. Someone asked me how to do it. What is 16th complement and what is 15th complement? So 15th complement is called as F's complement. What is F's complement? Subtract, same rule. There is no difference. Whatever may be the process, it is same. Whatever may be the complementary form. F minus F is 0. F is 15. 15 minus 2 is 13. A, B, C, D. A is 10. F is 15. 5. F minus 1. F is 15. 1 is 15 minus 1, 14. A, B, C, D, E. What is that? E, 5, D, 0. If you want 16's complement, add E5, D0 plus 1, which will give you E5, D1. That's all. Now your doubt is clear, Krishna? So what is this BCD code? We call this as, till now they have not given. See, if we have R, you have only R's complement, not more than that. Any number system with base R, we can have R and R minus 1's complement. So please listen. Don't worry, Aditya, just wait for some time. We are not doing subtraction at all. Subtraction will come next. Okay. Binary coded decimal. Okay. So BCD is nothing but binary coded decimal. Okay. Even though your computer is very much comfortable with binary, that is ones and zero, but in your day-to-day life, you are using what? Decimal only. You are using what? Decimal only. So decimal, if you are able to represent the number, decimal number as it is, or if you want to store the decimal number as it is, okay, so then we should use this kind of format called BCD, because your memory, everything is binary nature only, on and off only. So here what I will do is, suppose I have a number 23. 23 in the binary, 23 is, let me write next line better. Suppose you have the number 23. What is the binary equivalent of 23 by dividing with 2 and all those stuff you do it? 8421 code say I have written it as 10111. Is it okay? 16 plus 7 is 23, right? So now listen here. Now listen here. 23 base 10 is equal to this one, binary. In BCD, you don't write like this. What you do is 2 separately. 2 is how much? 0, 0, 1, 0. 3 separately. 3 means how much? Okay. This is how you represent 23 in the BCD. What is the advantage? I will come to that. Just there is another way to represent is, please listen. 2 is 0, 0, 1, 0. 3 is 0, 0, 1, 1. Here we add 4 more zeros. Why you are adding 4 more zeros? With respect to memory, each digit is stored in one memory. One memory location is 1 byte. 8 bits is 1 byte. Okay. 8 bits in 1 byte. Okay. Is it clear now what I am saying? This is how you go for BCD. What is the advantage? I will come to that. First, you understand the process. This is what we call packed BCD. And this is what we call unpacked BCD. Just have a glance again. You can understand. Krishna, hexa and decimal both in 4 bits. We are not talking about hexa here. It is only decimal. Your number is 0 to 9 only. Each digit is in the range of binary coded decimal. This is for decimal. Each digit is coded as a binary number. BCD. Okay. Each decimal digit is represented separately with 4-bit binary equivalent. Now please see, 23 is binary mein, you should do normal binary operation this much. In the BCD we write 2 separately, 3 separately. You may take 4 bits to represent 2 or 8 bits to represent 2. Similarly 3 also. If you represent 8 bits, 1 digit, it is called unpacked BCD. If you represent 4 bits, then it is called packed BCD. Is it clear everybody? Advantage I will come to that. Okay, okay. Hi Anupama. Okay, fine. Okay, very good. And now listen here. This is generally one in memory. Each location will contain one digit. Okay, it may be easy to retrieval and all those things. Now come to here. One small practical example I will show you where you can use this BCD. For example, you might be seeing this kind of displays. 7 segment display we call it. Okay, so it is having the name A. How many LEDs are there here? A, B, C, D, E, F, G. Okay, so here A, B, C, D, E, F, G. Please wait. Okay, right. Seven LEDs are there. You want to represent the number 0. 0 means all LEDs should on except the middle one. Yes or no? 0 is represented like this. What is the code here? All should be 1 except this. Similarly, you want to represent 9. How to represent 9 here? 9 is all LEDs except E. Except E. Right. So in the computer, I should write code like this for every number, yes or no? Then only computer can display your results. My answer is 55. Computer should display it as 55, means it should give ones and zeros to display the 55. Okay. So for suppose I want to represent 55 here. What is 55? Binary number 55 you take. Please listen. Binary number if you take 55, 55 is equal to 32, 16, 48, 48 plus 7. I hope so. 1, 2, 4, 8, 16. Right. So this is your 55. So whenever this comes, you should display. So one 7 segment is not sufficient. You should give the second 7 segment, and you should develop whenever this comes. You should display this another code to be written. Okay. Please understand now. I have a 7 segment display. If you are computer science, just leave it. Okay. If you are ECE, concentrate. This is your 7 segment display. It can display your results like this: 0, 1, 2, 3, like this. I hope you know this. You have seen a number of times this kind of displays, yes or no? So whenever your number is 0, your computer should give these inputs to the segment, 7 segment display. Similarly, whenever your number is 9, it should give these inputs 1, 1, 1, 1, 0, 1, 1. Then all those LEDs will be on, remaining will be off. Okay. Now for 55, one LED cannot do your job. One LED cannot. This is binary, please. Binary 55 is this much. Don't have doubt in this part. 8, 4, 2, 1, 16, 32. Okay, 13 plus 16 plus 4 plus 2 plus 1. This is 55. Okay, leave it. So here, what to do? You should have two 7 segment displays. You should give the code like this: 5 for first, 5 for another. Okay. Similarly, 56, 5 for 1, 6 for 1. Okay. So here, how many 7 segments are required? Please concentrate. Okay, two 7 segments are displayed. This we cannot avoid because display should display it like that. Now, codes, how many required? If you have, please listen. One display. One minute, please. 1 minute. I'll ask you. Tell me one by one. One 7 segment display. Okay. Forget about BCD. I am not talking about BCD here. Only binary. Only binary. Okay. One 7 segment. It can represent 0 to 9. Okay. We should generate 10 different codes. Up to this point, everybody clear? Okay. Now, if you have two 7 segments, then I need to give 0, 0, 2. I can represent 9, 9. So for 100 different numbers, I should generate 100 different codes. You accept this or not? Each code, this is code. Each code will on one particular LED pattern. Okay. Is it okay? Now, in this, if you don't have doubt, I can move further. Okay. What is your doubt, please? Please, Khan, please ask your doubt clearly. I can help you. What is your doubt in the last two lines? I am not talking about BCD. Forget about BCD first. Aman, forget about BCD. Forget about BCD. We are not talking, okay, about BCD. Just remove it from your mind now. We are talking, okay, your input is a binary number. Okay. What is the advantage or disadvantage? Here we are talking that part only. Okay. You have one. Don't listen this with BCD in your mind, my dear friends. Okay. Don't listen this with BCD in mind. Forget about BCD now. If we have one 7 segment display, it can display range is 0 to 9. Okay. So number of codes. How many codes I need to generate? 10 different codes. Codes are, you can say, patterns. Okay, please, those who understand, don't comment. Those who have doubt, I want answer from them. Okay, so that they will be getting clear. Those who have asked me, Khan, up to this point, you have no doubt, I think. I should generate 10 codes. Each code will on one particular LED. Okay, next. You have two 7-segment displays. So range is 00 to 99. Assume decimal numbers. So how many number of codes I need to generate? My dear Khan, please tell me. 100. Okay. Number of codes you need to generate is 100 if we represent in binary. Because in binary, every number is unique. You want to represent 10. You now assume you have 10 digits. 10 digits. How many you need to represent? How many codes you will generate? Is it possible? Yes, Magna, very good, correct. Okay, if you have 3 digits, 1000 codes. If you have 4 digits, 10,000 codes, like that. What is this code? You understand? That is the where you should give 1, where you should give 0 for the corresponding LED. Okay. So is it possible if you have 10 number of digits, 10 power 10 number of codes, you need that much amount of memory to store the codes only? Okay. So here you can go simply like this. If you have a number 25, don't represent 25 as a whole. Represent 2 separately, 5 separately. 345 is there. Don't represent 345. You represent 3 separately, 4 separately, 5 separately. What is the advantage? What is the advantage here? Packed or unpacked, so leave it here. Forget about your packed and unpacked. Here, that point is not about packed or unpacked. Okay, here you have only 9 different codes per each digit. Here you are treating every single digit separately. You are treating every single digit separately, not a whole number. You are treating every digit separately. What is the advantage? 5 is represented as 0 to 9. 4 can be represented in the range of 0 to 9. So any digit is in the range of 0 to 9 only. So I don't need 1000 codes here. I need only 10 codes. Only 10. Only 10. Only 10 different codes. Now you are happy? You understand the advantage of the BCD representation? Fine. So forget about packed and unpacked. Okay. So let's move further. Now listen here. In the BCD, we have, these are the different codes we are going to use. Okay. So please listen here. So here each digit is in the range of, in BCD, each digit in the range of 0 to 9. Okay, now see here, 0 to 9 I have taken. What are the BCD codes? 8421. Okay, is the standard, our binary only. Okay, suppose you need 5. 5 is 4 plus 1, na? So 5 can be written as 8, 4 plus 1. 6 is 4 plus 2. Here every position is having the weights of 1 to 4, 8. Is it clear this point? 7 is 4, 2, 1. 8 is 1, 0, 0. 9 is 1, 0, 0, 1. Is it okay? Fine. So now listen here. Similarly, similar to 8421, we have another code called as 2421. Okay. What is 2421, sir? 2421 code, positional weights are how much? 2 only. Okay. So here 1 is, just listen, 1 is represented directly, 2 can be represented as 1 0. Then you get the doubt, sir, why you take 1 0? Why not 1 triple 0? Because 1 triple 0 is also weight is, please understand, every position is having a weight. 1 triple 0 is also 2 only, 0 0 1 0 also 2 only. Both are correct. But I will give you one restriction here, just wait. Next, 0 0 1 1 3 4. 5 means 2 plus 1 is 5. That's why you get this one. 6 is 2 plus 4. Like that, all ones will give you 9. Okay. Next, come here. 8 4. It is negative weights. It is a mix of positive and negative weights. Okay. So 1 is 4 minus 3. 1 is 4 minus 3. 2 is 4 minus 2. 3 is 4 minus 1. What is 4? 4 only. 5 is 8 minus 3. Like that you can represent here. The next one is excess 3. Excess 3 means instead of 0, you should write 3. Instead of 2, you should write 5. Just add 3 to every number here, you get excess 3. If you add 3 to this all, you will get excess 3. Now you will get the doubt. Sir, why excess 3? Why not excess 4 or excess 5? Why we like excess 3? Yes. Why these different ways? Your question. Second question is, sir, 2421 is in that why you take 0010? Why not 1000? Or 6 can be 6. Suppose you take 6, you may get 11100 or 0110. Which one I need to choose? Okay. So now, yeah, you can take 0101 also as a 5. Why can't we take it as 5 directly? All these doubts will be in your mind. Let me clear all the doubts. Just wait. Here, one particular observation you need to have. What is the complement of all zeros? What is the complement of all zeros? Complement of all zeros is all ones. It is here. Okay, na? What is the complement of 0001? What is the complement of 0001? 1110. It is here. Similarly, what is the complement of 0010? 1101. It is here. What is the complement of 0011 and 01? You can see this and this are complementary to each other. Second one and second last one are complementary to each other. Third and third last are complementary to each other. Will you accept this or not? What is the advantage? I will explain. First, you accept it or not? Same rule is here also valid. Here also valid. Okay, here also same rules. They are complementary to each other. That is the reason why I take some. Why don't we take some random numbers here? Why the what is the speciality of 842 minus 2 and 1? Yes, all these are called as what is the another name of all of them? All of them are called self-complementary codes. Okay, so let me write that. What is the name for this? Meaning I will explain. What is the name for this? Self-complementary code. It is called as a self-complementary code. Okay, why it is called self-complementary? Listen. In a self-complementary code, sum of weights equal to 9, but excess 3 is not having any weights. Don't worry about that. Excess 3 is not having any weights. Only these are weights. You add these weights, 2 plus 4, how much? 6. 6 plus 3, 9. 8 plus 4, 12. 12 minus 3, 9. That is one thing. And 9's complement is equal to 1's complement. So what is the advantage of this representation? 9's complement can be done easily by 1's complement. 1's complement don't need subtraction. Inversion is sufficient. 0 becomes 1, 1 becomes 0. But here, that is the advantage. For example, let me take excess 3. Excess 3, what is 5? What is 5 in excess 3? 1 triple 0. Okay, 8, that is 1 triple 0. What is 9's complement? 9 minus 5. How much it is? 4. 4 means excess 3. 4 is 0 triple 1. Okay. Directly take 1's complement. In excess 3 I am talking, not in binary. Don't okay. What is the 1's complement of this 5? We represent by bar here. Both are same. So you have accepted this or not? Okay, so that is what we call self-complementary code. That is the reason we have taken this particular pattern here such that it will satisfy self-complementary code. This and this are complement to each other, like that it will satisfy. This is the reason why excess 3 is there, not excess 4 or excess 5 or excess 6. Okay, so you should remember what is suppose excess 3, 5 is 1 triple 0. What is the 5 in excess 3? 5 is 1 triple 0. Okay. So what is the 9's complement of 5? What is the 9's complement of 5? 9 minus 5. Subtract the number from 9. Subtract the number from 9. That's all. 9 minus 5 is 4. Okay. So what is 4 in excess 3? What is 4 in excess 3? We are speaking in excess 3 only. What is 4 in excess 3? 0 triple 1. Okay. Next, lastly, directly you do the complement. Same answer will come now. Directly you take the complement of 1 triple 0, it is 0 1 1 1 only. So if you take 9's complement or 1's complement, your answer is same, then it is called self-complementary. Excess 3 is nothing but add 3 to every number of the 8421. Excess 3 is nothing but if you have 4 na, write it as 7. If you have 5, write it as 8. Now it is clear? Okay. Every time when it is a self-complementary. Okay, you take any number, it will be true. No doubt in it, Deep. You take 345 or 354 in the excess 3. 3 is how much? 5 is how much? 4 is how much? 7. Okay. You take subtract this number with all 9s. Okay. Yes, always true. Subtract this number with all 9s. All 9s minus 354. What is that? 6, 4, 5. What is 6, 4, 5 in the 9s in the excess 3? 1 0 0 1. 4 is 0 triple 1. 5 is 1 triple 0. You take complement of this, you get 100% same answer or not? Tell me. What is the complement of this? 1001, 0111, 1000. That's what I am saying. Any other doubt, please ask. 84 minus 21 also same. Weights are negative, that's all. Suppose Deep in 84 minus 2 minus 1, you want 5. 5 is represented as 8 minus 3. 6 is represented as 8 minus 2. Okay. What is 2 and 10's complement? Meghana, I didn't get you. Yes, you can use any one of them. How many are possible? Those many you can make. Simran, every self-complementary code is having one advantage here. Here, please see. Let me explain advantages of these three. Okay. So, firstly, what is the advantage of 9's complement? In computer, You want to perform a minus b, it can be written as a plus 9's complement of b or a plus 10's complement of b. Okay. Is it clear what I am saying? Is it clear or not? Please tell me. Okay. What is your doubt, others? Please ask your doubt clearly. I can help you definitely. My dear friend Magna, you can see in BCD codes, your range is 0 to 9 only. There is no 10. There is no 10 here. Your every digit is 0 to 9 only. Okay. If you want 10, we represent as 1 and 0 separately. Your doubt is clear. Anuj, 84 minus 2 minus 1. There is no logic here. Please see. Add these numbers. Wherever 1 is there, you take that number. Okay. Suppose here 4 ones. What is the equivalent? Add 8 plus 4, 12, minus 2, 10, minus 1, 9. Okay, there is no logic here. Just add the numbers. You have the weights, na, corresponding weight here. 4 is there. What is this value? 0. Is it clear? Let me explain again. You have 8, 4, minus 2, minus 1. If you have this number, forget about that, everything. What is the equivalent? Now, those who have doubt only comment, not others. Now, what is this number is? Just add these two. What is that? 8 minus 2, 6. If you have, this is not there in our representation. Okay, but you have this one. Add all, which will give you 9. Add this and this, what you get? 7. Same logic for 2, 4, 2, 1 also. If you have like this, it is 2, like that. Here you can have two possibilities in 2, 4, 2, 1, but upper half and bottom part must be, upper part and bottom part must be self-complementary. Here excess 3 means add 3 to this number. If you have 0, write it as 3. If you have 1, write it as 4. If you have 9, write it as 12. Okay? All doubts are answered? Now listen here. Excess 3 code is both self-complementary and also sequential code. That is, if we add 1 to previous number, we get next number. If you add 1 to the previous number, what will you get? Next number. Let me help you or explain you with the help of this example. You add here 1, next number will come or not? You add here 1, next number will come or not? This is called as a sequential code. But here, please see, if you add 1 to this number, will you get the next number? Please comment. If you add 1 to this number, will you get the next number? No. These are not sequential. These are not sequential. This is a sequential. Okay. So please listen 1 minute. Sequential. Okay. Weighted and self-complementary. 3 classifications you can make. Point. If you have 8421, it is a sequential, it is a weighted but not self-complementary. If you have 2421, It is not sequential, but it is weighted and self-complementary. Similarly, 8, 4, minus 2, minus 1 also. What is the advantage of access 3? Here it is a sequential, not weighted. Not all three, not all three. It is not weighted. Weighted means position is having a meaning now. Here 1011 is there. Each position is having one meaning. But for access 3, that positional values are not there. Yes, Asif, you can interchange. There is nothing wrong. You can generate a number of codes. These are most commonly used regular codes. Okay, you can make your own code, nothing wrong. So is it okay then? Can I proceed further? Okay. No, Habib, it is not weighted. We are adding excess 3 now. Your weights will be difficult. 7 is like this. 7 is 1010 in excess 3. Where is the weights here? Which weights you want to prove? Habib, if you take 8421, it will be 10, not 7. No? Yeah, you can make it. What is the problem? Okay. So the next one, how to add BCD numbers. How to add BCD numbers. You have two BCD numbers. Let us see how to add two BCD numbers and get the result. Good evening, Brajesh. When we add two BCD numbers, okay, using binary adder, normal addition only I will do, but I want result. Your whole system should be according to that Asif. Okay. When we add two BCD numbers using a binary adder to get a valid BCD result, we need to perform these two. What are these two? I will explain. Just take one example first. I have a number 34. Wow, Amit. 66. Now, listen. 6 plus 4 is how much? 6 plus 4. Please tell me here. 6 plus 4 is 10. 1 plus 3 plus 6 is again 10. 100. Okay. You have accepted. Now, I write 34 as in the BCD. 34 is 3 separately, 4 separately, 66 also, 6 separately, 6 separately. Now add these numbers, you get 0, 1, 0, 1. There is no here 0, 1, 0, 1, 0. If you see here, every 4 bits is called nibble. What is that? 4 bits is called nibble. Okay. Yeah, 1, 1, 1, 1, 1. Okay. It is not LSB, it is called MSB, it is LSB. So this is nibble. From here to here, whatever you are getting, it is having one name called auxiliary carry. From here, whatever you are getting, this is what we call main carry. Carry from MSB, most significant bit. Okay. Now listen. I want 100, but I got something wrong answer na 09A. Wrong answer. I need BCD answer. I want. I'm adding two BCD numbers. I want result also BCD only. But I got something wrong. I don't want. Now, how to modify this to get my required answer? Okay. Now, everybody. Now I am giving you just the rule directly. When we discuss binary arithmetic circuits, I will give you logic also. Okay. Now, what I will do is here I need to add 6. When to add 6, when not to add 6, I will tell you. Okay, 0. 1 plus 1 is how much? 0. 1 plus 1 is sum 0, carry 1. 0. You add this one here. Now 1 plus 1 is how much? 0. I'm wrong. Right. So again you got this much. But this is also not right now. What is this? Greater than 9. 9, your result should be less than 9 only. Any 4 bits should be less than 9, but I got more than 9. So add here also 6. So what you are doing, I'm not able to understand. Don't worry, just wait for some time. Now it is all zeros. It is 0. 1 plus 1 is sum 0, carry 1. 1 plus 1, sum 0, carry 1. 1 plus 1, sum 0, carry 1. Now you got the required answer. Okay, right. So this is your 1. This is your 0. This is your 0. You got the required answer or not? First, you got the required answer or not? Tell me. Whether process, so don't worry about it. I will explain it. You need the representation like this. After doing this, some mathematical manipulations, you are able to get that or not. Okay. Okay. So first, you got the valid answer. Now, what I have done, I will explain. Listen here. First, listen, Krishna. I am explaining now only. I have not explained it. Okay, please listen. We need to add two BCD numbers using a binary adder to get a valid BCD result. What we need to perform? If lower order nibble meaning is 4 bits greater than 9 or auxiliary carry equal to 1. Any one of these conditions are satisfied. What is that? See here. After adding, check lower order nibble. What is the lower order nibble here? 1 0 1 0. If it is greater than 9 or this auxiliary carry equal to 1, any one of them is true, add 6. Here it is greater than 9, I added 6. Up to this clear, Khan and Krishna? Up to this clear? Okay. So after adding this, what you got it, check it. Firstly, here check it. Is it greater than 9? Is it greater than 9? No. Is this carry 1? No. If it is not true, don't add here. Only add here. Now you got some result. Check here. Is it greater than 9? Is it greater than 9 or not? Tell me here. Yes. Add 6 here. Then you get the final answer. So simple rule is simple. Listen here. If you have result greater than 9 or auxiliary carry equal to 1, add 6 to the lower nibble. If higher order nibble is greater than 9 or carry from MSB equal to 1, add 6 to the higher nibble. Okay. So valid result should not get any 4 bits greater than 9. That is the required point. Okay. So after doing the addition, is it greater than 9? Yes, add 6. After that, check it. You got here greater than 9, add 6. You should check two things. Greater than 9, you should add both 6s. Here also 6, here also 6. Greater than 9, and also you should check this also. Any one of them is true, add 6. Or simple rule, please listen. Instead of doing all this, one simple mind, in your mind, you keep it. You know the addition of these two? Until you get valid result, you should do. You know the addition of the 100, na? So forget about all these things. Do anything, get this answer. Then you can make your own rules. Do whatever you want and get this answer. Yes, 8421 only. Okay, so this is the reverse engineering you can do. So why 6 is added? Why 6 is added is the question asked. I already told. I will tell you here process. Reason we will explain in the arithmetic circuits part, because there I will again help you with the subtractions, additions everywhere. There I will explain this part. Okay. Why 6? Is it 6 true for every case or not? Everything we'll discuss. Just wait for some time. In the arithmetic circuits topic, we'll be discussing this part. Okay. Because the difference between 1 0 and this 1 0 1 0 is 6, we'll be adding this. That reason I will explain clearly there. Okay. Let me repeat this fastly. You add two BCD numbers. You add two BCD numbers. After getting the result, check two things. Is this greater than 9 or this value is 1? What is auxiliary carry? After this addition you are getting here, that only you should check. In any one of them is true. Okay, any one of them is true, add 6 here. Similarly, check here also. Is it greater than 9 or auxiliary carry equal to 1? If any one of them is true, add 6. Here it is not true, I have not added anything. First listen, when I am explaining, listen, then you ask your doubt. Suraj. Now, second time you add, don't check the auxiliary carry. Second time you add, don't check anything. Second time addition, you check only if it is greater than 9, add 6. If it is greater than 9, add 6. Okay. That's why what I said, you make your own rules. Don't worry to remember all these things. Get your result. That's all. Suraj, your question is answered, na? Second time, don't worry about your auxiliary carry. Both are greater than 9. Here also add 6. Nothing wrong. Both lines will add in that case, Rishi. So let me take one example more so that you will be more comfortable. 65 and 73 or 78 you take. 5 plus 8 is how much? 13. 14. Now you will be more comfortable after this. 6 is how much? 5 is, I am taking 8421 BCD code. 7 is how much? 8 will be. Now add 1, 0, 1, 1. Here you get 0. Again 1. This is 0, 1. 1 plus 1 plus 1 is 3. 3 is 1, 1. So you get some here, carrying it, and 1. So now this is your auxiliary carry. This is your carry. As you asked earlier, here this number is greater than 9 and this number also greater than 9. What to do, my dear friends? Tell me. Add 6 in both the cases. What is the answer? 1, 1, 1 plus 1, sum 0, carry 1, sum 0, carry 1, 1 plus 1, sum 0, carry 1, 1 plus 1, sum 0, carry 1. All three ones. Sum 1, carry 1. This is 1, 4, 3. Your favorite number, right? What here? No replies. Right. Oh, Corona में गया क्या हबीब? That only difference is representation. Okay, here every single digit is represented as a 4-bit binary number, and result I have explained, Kumari. Okay, reason why we are going for BCD I have already explained. So next, generally it is done in 2's complement magna. It depends on your particular application. Suppose your result is having to be displayed by 7-segment displays, generally they will convert into BCD and represent, which will make the representation or hardware will be easy. In general, in your microprocessor internally, most of the microprocessors, it is a 2's complement arithmetic only. So the next one, excess 3 addition. So the rules are not same everywhere here. For excess 3, the rule is similar, but see here, if there is a carry or auxiliary carry, add 3. If there is a carry or auxiliary carry, Okay. What do you mean by both modes, Sura? Whatever you write, it will take, but internally it is binary only. Okay. If there is a carry or auxiliary carry, add 3 to the corresponding nibble. Otherwise, subtracting. This is very simple. This is very simple. See here. You have the numbers 23 and 49. 1 minute. Let me write it. Next slide I will write so that you have a number 23. You want to add it to 49. So 9 plus 3 is how much? 2. 1 plus 2 plus 4. Here 1 plus 2, 3. 3 plus 4, 7. Now listen. I am doing it in excess 3, my dear friends. What is 2? What is 2? Comment. Yeah, 0, 1, 0, 1. Very good. 2 is not 0, 0, 1, 0. It is excess 3. 3. 3 is next. What is 4? What is 9? Okay. So now it is 0, 1, 0, sum 0, carry 1, sum 1, okay, carry 1, sum 0, carry 1, sum 1, carry 1, and 1. What you need to check here is not, forget about previous rules. Here rule is check only this thing. This is auxiliary carry, na? And what is the addition of this? Yeah, only those two things we need to check. Yes, auxiliary carry is 1, add 3. Carry is not there. Subtract 3. Subtract 3. Be careful here. Rules are different. So 1, 1 plus 1, sum 0, carry 1, 1, 0. Next, subtract 3 from this. 1 minus 1 is 0. You take the borrow, it will become 2. 2 minus 1 is 1. 1 is given, nothing is left. For subtractions, don't worry. We'll discuss clearly in the arithmetic circuits again anyway. Now tell me what is 1010? Comment please. Everybody comment. What is 1010? Is 10 actually, but in the excess 3 it is 7. What is 0101? It is 5. In excess 3 it is 2. You got your answer. Okay. So initially, after up to few 3-4 classes, you will be getting the doubts like this. But once you will be in sync with me, then later on you will not be getting any kind of doubts. Okay, don't worry about that. And I am happy to clear all your doubts at any point of time. So this is okay. So shall we proceed further to one more important code? Yes, Simran. If there is a carry, add 3. No carry, subtract 3. Okay. Rishi, you can try this. If you have any difficulty, tell me. 73, yeah? Try this. In here, both the cases, you should add 3 and try this part. Another example if you want. Just give a try. Next. Something wrong, right? Nidhi, just wait. I told already after the end of every chapter I will share, and you can also take the PDF of this. I hope you know after the end of the class, PDF is available with annotations. You download it, and I will also provide PDF. Why 7? 1010 is 10 na. Excess 3 mein 10 is nothing but 7 only. Nisha. Sorry, Nishita. I told you, Mahinder, subtraction we discussed very clearly in the arithmetic circuits part. Don't worry about it. And in the doubt session also, I will take more examples of that. Okay. Next. So the next one. Khan, I told na, tomorrow onwards we will be getting DPP also. Fine, Sushil. The next one is a gray code. This is very important. It is a unit distance code. That is between any two adjacent numbers. Adjacent means side by side. Okay. Any two adjacent numbers, only one bit changes. Between any two adjacent numbers, only one bit changes. What is its use and all? We'll finish gray code and we can stop the class. Okay. So what is first? Let me write what is. I mean, let me give you the formula of the gray code. Then I will prove all these conditions, its advantages and all. What is the gray code? Is if you want GI from the binary, you want to convert gray code from binary. Okay. GI is equal to BI XOR with BI plus 1. Again, 1 minute, 1 minute. If MSB. What is GI? It is BI XOR with BI plus 1 otherwise. Here, what is this symbol? We discussed in the logic gates topic. It is called XOR gate. What is this symbol? What is this symbol? XOR. What is XOR operation? Listen. Both same output 0. Both different. For timing, you remember like this only. Everything we discussed clearly in the XOR gate operation in the logic gates. Okay, both are same, you get 0. Both are different, you get 1. Let me take one example. Suppose I have a binary number 1011. What is the corresponding gray code? 1011. What is the corresponding gray code? Take the first number as it is. Okay. Now listen. You take these two and apply XOR operation, you get the next number. XOR means different. Both are different, give 1. Both are different, give 1. Both are same, give 0. This will give you gray code of 1011. I'm not saying there is unit distance between these two. Forget about that. That I will come to that. Okay, this is how you get gray code of any number. Okay. So reverse. What is reverse? I have discussed the binary to gray now. So how to get gray to binary? You have gray code. How to get the binary? First, if it is MSB, take as it is. First bit is to be taken as it is. And for other cases, it is GI XOR with BI plus 1. Okay, GI XOR with BI plus 1. I will give you the example. Same example we take reverse conversion. Suppose you have 1110. What is your gray code? What is your gray code? 1110. How to get the binary number? Binary first number take as it is. Now you take these two and apply XOR. One XOR and one. Both are same or different? Tell me. Same or different? Same or different? Ah, 0. Here both are same or different? Different. 1. Both are same or different? Different. If it is different, you will be getting 1. So you got back the same answer, right? So this is gray and binary conversion. Let me explain you the advantage of this. Okay. Or here I can show this with the help of how to get the gray code is. So suppose you have a binary number B3, B2, B1, B0. Later you can understand this easily. It is G3 is as it is. B3 can be obtained by XOR. XOR is represented like this. What is XOR? Okay, is both are different, you get 1. Both are same, you get 0. XOR gate is represented. What is gate? Everything we discuss in the next chapter. Okay. This is the gray code 1. Gray code of this one. This is the circuit to make this. Similarly, if you have gray, how to get the binary? G3 and B3 are same. You take this and apply B2. Sorry. Apply G2. What you get? It is called B2. Wait, G1. Nidhi, you want circuit or you want the equation? Equation. Which one? Binary to gray. So first bit as it is you copy. First bit as it is you copy. Then these two XOR will come here. These two XOR will come here. You do XOR of these two and write it here. XOR means different now. 1. These two, write it here. These two, write it here. Both are same. That's why you should write it as same. Okay, Nidhi? Okay. So what is the advantage of this? Suppose you write a gray code of first 16 numbers. How to write gray code of? Now, how to write gray code of first n numbers? Okay. Will you take every number and apply this operation? It will take you so much of time. Don't do that. I will give you easiest way. Okay. So first start with your 0. If it is 0, take here 1. If it is 0, take here 1. Now take its mirror image. Mirror image, please concentrate. What is the mirror image of this? What is the mirror image of 0, 1? 1, 0. यही तक है. So up to this clear now. Now you take here 2 zeros, 2 ones. Is it okay up to this? If you take this one, this will give you gray code of first 4 numbers. Again, see here. Again, take its mirror image. Okay. So first take 0, 1. Take its mirror image. You get 1, 0. First half is all zeros, second half is all ones. Simple rule. Then again, take this whole mirror image. Whole mirror image is 1, 0, 1, 1, 0, 1, 0, 0. Then again, what to do? Take all zeros here and all ones. This process can be repeated up to whatever the number you want, you can do up to that. Okay. So this will give you gray code of 0 gray code, 1 gray code, 2 gray code, 3, 4, 5, 6, 7. For example, listen here. What is 7? First listen completely, my dear friends. What is 7? 111. What is the gray code of 7? What is the gray code of 7? This is binary. Okay, what is the gray code? First bit you should copy as it is. Then these two XOR. 0, these two XOR 0. You got the same here or not? Every time, okay, if the examiner asks you 0 to 15, don't write all the 15 and do this process. Simple process. Now see here. What is the simple process? Start with the first number 0 and 1. Take its mirror image. Concentrate here. Whatever you have here. Mirror image ka matlab kya? What is the mirror image meaning? Just take its reverse. If it is 0, 1, take 1, 0. First half all zeros, second half all ones. Okay. Then you have this number, right? This 4. Take its mirror image. 1 0 1 1 0 1 0 0. Process if you understand or not. 4 zeros, 4 ones. If you want first 16, take its mirror image. 8 zeros, 8 ones. If you understand the process, please type yes. Now you observe here any two numbers have only 1 bit difference. 0 0 0 1. After that, if you take 0 0 0 1 1, what is the advantage? Only 1 bit is varying. Remaining all bits are same. Take any two, only 1 bit varies. Any two adjacent, only 1 bit varies. Yes. Yes or no? Okay. Suppose if you take binary, what is the advantage? If it is 0 0 0 0 1 1, after that what you get? 1 0 0. More number of bits are changing at a time. So if they change, what is your problem, sir? Why you don't like if you have more number of changes? It is not my personal problem. Please understand. If you hear, what is the advantage here? Let me give you with one practical example. मेरे पास you have one kind of angular displacement. Okay, this is like this. It is rotating. Some angular displacement is there. Okay, here 1 2 3 4 5 6 something. Your angular displacement, whatever getting angular displacement, this is converted into digital format for processing. Okay, I am getting this angular displacement like this. 1 2 3 something, whatever may be the angles you will be having. This angular displacement of a particular some kind of system is converted into digits and those are stored. If I take binary, what is the disadvantage? If you have 3 have 0 0 0. After 3, if it has become 4, 1 0 0. In between you see there is small disadvantage. All bits may not change at a time. Will you accept it or not? All bits may not change at a time. If you take binary representation here to store the values, all bits may not change at a time. First, suppose this bit has changed. Second, this bit has changed. Lastly, this bit has changed. Then before 3 and 4, you got some two unnecessary transient tree values. Ambiguity is coming. We call it TX means what? Transient. Or ambiguity. This will be there if you take binary. But for gray code, this problem will not occur. Why? See here, it's 3 is 0 1 0, 4 is double 1 0. So 3 is now 3 to 4 transition, only one bit has changed. So there is no disadvantage here. In between, you don't have this kind of states here. Okay. So no, what is that? Transients. No ambiguity. Ambiguity means doubt. Yes, say code wheel, you can say code decoder, whatever may be. Okay. Whatever may be. Is it clear what I am saying? So this is the advantage in the gray code because it is a unit distance code. Only one bit changes at a time. In between, intermediate states will not happen and there will not be any errors between one state to another state transition. When it is changing its state, you don't get any problem, any state transition or transients. I hope its time is up. Okay. So Nidhi, just wait. Let me give you one question. Yeah, let's have one question. Not every time. It is your requirement, Bhavesh. So now, because we have discussed this, you can answer it very happily. Otherwise, if you read this question itself, by seeing the names, you can leave. Now you see this much easy. The question is larger radar installations. It is required to translate angular position of the shaft into digital information. So just wait. This is most achieved by a code wheel for an ambiguous sensing of the shaft. Which of the following? So let's have a poll for fun, so that 100% I will be getting here. So don't make unnecessary wrongs. You are also playing, right? You don't want 100%. Oh, error. So happens. So computer is also playing error here. 9546 101% it is showing. Sometimes it happens. So okay, you can see your results. At the end of the day, your answer is gray code. Okay, for an ambiguity, we'll go for the gray code. That is in between two positions, you don't get intermediate states. Now let me answer Nidhi's question. I hope everybody know it is a IES question. Okay. So now please see, Nidhi, when you are moving here, 1 to 2, 2 to 3, 3 to 4, I want to convert this into some kind of digital format. So I am writing 3 to move, it is 4, it is moving. So 3, next number is 4. So 3 and 4 in between, if you change one bit at a time, okay, because all bits may not change at a time because of the internal delays. So 3 to 4, 3 bits are changing at a time. All the 3 may not change at a time. Na? So first this bit may change, then this bit may change, lastly last bit may change. Not exactly deep. Some previous questions, some with my experience, some depend in different sources. Because I am teaching from 9 years, I have my own notes. So from that only, I made already everything, get it typed. Today also, whatever this required slides, everything I prepared on my own. I sit for some time before every class to type so that it will save your time. Because suppose you see here, if I write every single point, if I make this table, it will take your half an hour. Okay, I don't want that. We can deliver more if I make it fast. Little, I mean, by typing. So I hope Nidhi, your question is answered here. Thank you, thank you. I am from EC and also CSC mixed. Okay, originally EC. Thank you, thank you. Okay. So whatever kind of doubts, general doubts, whatever doubts you have now, you can ask. BPP, I will be providing you from tomorrow. Okay, your first chapter will be completed tomorrow. I will be providing the necessary DPP tomorrow. Okay. So first chapter and I will start Boolean algebra also tomorrow. And the day after tomorrow, we'll be doing more number of questions. So whatever your DPP questions and all those things. So ready, most of the people have already joined in this group. Okay. So for the Telegram channel or your doubt solving everything, you can message me on Unacademy app. I will take you. I will give you all the necessary links. See, Asif, we are saying sequential. Okay, between any two successive only, not between first number and last number, which is impossible. One bit changes between two successive. Thank you, Behra. Thank you, Aditya. Nishita, it depends because you are asking in what we call objective or conventional. Objective, you can expect good number of marks. Earlier, they used to give 20 marks from this before pattern change. Yes, ready. After the end of the chapter, every end of the chapter, I will provide handwritten also. But you can download slides also. Slides I made properly, perfectly, so that if you read slides also, you will not face any difficulty. So any other general doubts, whatever DPP, anything. Otherwise, we can end the session. Thank you, Akshat. Thank you. So good night. Let's meet tomorrow at the same time. So be regular to the classes, be on time. If you miss the beginning or some part, you will be missing the logic. You may be facing difficulty in the classes. So be regular to the classes. In the drive, I don't provide until end of the chapter. After end of the chapter, I will update. If someone asked regarding drive, I don't provide before the class. I will provide after the class, end of the class. End of the chapter, I will update regularly. Thank you very much. Just please rate the class. Thank you very much. We'll meet tomorrow. Good night.